Hello and welcome to your A-Levels Physics class. Today we'll be looking at the Doppler Effect. The Doppler Effect is a really interesting phenomenon because it's something that you can and probably already have experienced in real life. It's how the sound of sirens, for example, appear to become higher and higher pitch as they approach you, but then get deeper and deeper as an ambulance drives away. But it's also how speed cameras capture the speed of moving cars on the highway. But the Doppler effect can also give you an understanding of the motion of stars. And I've already written down the definition of the Doppler effect for you, whereby it is the change in the observed frequency of a wave due to relative motion between the source and the observer. Now what this means is that when you look at the word observed frequency, this means that the actual frequency is actually constant. So the frequency that's coming out of the source is actually constant. But what changes is the frequency that is being observed by the observer. And this is due to this relative motion between the source and the observer. The relative motion here implies that there is greater or less distance between the source of the observer, which means that they could be coming together or moving apart. Now, let's see how this works out in real life. So, let's say that this black box over here is a moving speaker. And then there's you, a stationary observer. Now the speaker is moving towards you with a certain velocity v. And at the first instant in time, the speaker releases sound waves, as a speaker does. And these sound waves approach you, and they approach you with a certain frequency, S stands for source, and a certain wavelength, S. But now, at the second moment in time, what you notice is that as the speaker moves forward, it releases the same sound waves that has the same frequency and the same wavelength. But what happens now is, you as the observer, you observe variations in the characteristics of the sound waves. So as you can see here, based on this wave plane, the frequency of the sound waves, FO, which is the frequency that you observe, appears to have increased, while the wavelength of the sound waves that you observe appears to have decreased. You can see the wavelengths are shorter now. And what this means for a sound wave is that the pitch is now higher. And this pitch is how you hear sirens, for example, becoming higher and higher pitch as they drive closer to you. Now let's look at that example deeper. Now this is an ambulance, and this is the observer that the ambulance is approaching. And this is the observer that the ambulance is moving away from. So what you notice now is that as the ambulance drives towards this observer, these sound waves sort of come closer and closer together, so they appear to be compressed. And this results in that higher pitch because of an increased frequency for observer 1. So this person here is observer 1. But now for observer 2, what happens is because the ambulance is moving apart, the wavelengths appear to be stretched out. And this means that there's a decrease in the frequency for observer 2. But in actuality, the frequency of the siren that is coming out of the ambulance from the noise of the ambulance is actually constant, which is frequency of the source. So when you look at this, you see that in actuality, the frequency of the source is the same and has always been the same, but this is smaller than the frequency that is observed by observer 1, but it's bigger than the frequency that is observed by observer 2. So this means that for observer 2, they observe a lower pitch. Okay. Now, how does this apply to stars that I mentioned earlier? So let's say we have this orange star. Now, then there is you, the student. Now with stars, it's the same idea, but now when the star is moving towards you, its waves get compressed in the same way. They appear to be compressed as if the star was moving towards you. And because of this, the wavelength decreases and the frequency increases. And this means a color change when it comes to light waves. And this is known as a blue shift. Because with light, as your wavelength drops, the light appears bluer and bluer. Now what happens if the star was moving away? If the star is moving away from you, then the wavelengths appear to be stretched out. And because of this, the light appears to be redder and redder. This is because the wavelengths increase and the frequency decreases. This is known as a redshift. So astronomers have noticed that you can actually tell when a star is moving closer to the Earth or moving further away from the Earth through the shifts of light that is observed. And this is really, really interesting because this is how astronomers observed and discovered something known as binary stars. So binary star is where you have two stars that orbit one another in another solar system, for example, outside of our solar system, and how an exoplanet can orbit around those binary star systems. Now, the reason this could be observed is because as one star moves closer to the Earth, you notice this blue shift from the light that comes out of the star. And as the other star moves further away from the Earth, you notice a red shift that comes out of the light from the star. And this clearly showed that these two stars, first of all, that there were two stars because of these different shifts that were being observed from this region, but it also demonstrated that these two stars were orbiting one another, or they were orbiting this fixed point. And any nearby exoplanet was just following around in this orbit around that fixed point between these two stars. So that's the Doppler effect, and how you can observe it in sound waves through sirens and the variations in pitch, and in light waves through the variations in color. Thank you.